Hi, these are just some introductory comments uh, on getting started with this web-based course on digital food physics and modeling. It simply tries to say what do we mean by this digital food physics and modeling and why do we care for it. So first, why do we care for food physics? It is something worth talking because historically we know food science means, for example, food chemistry and certainly a food microbiology. But then when it comes to food physics, things are not that well developed and organized. And so the food physics is sort of been the poor cousin. But if you look at, for example, how um, science is organized and these are sort of generic figures, so you see there's sociology at the top, psychology, biology, chemistry, and then physics is also there. So reality, when people discuss reality, they very much have food physics, physics at the bottom. So food physics is also important. It's just not been, um, nicely organized and put together. A lot of work has been done. And so our goal in this course is going to be to get into more of the food physics. So physics likes some sort of universal framework like gravity. And so in case of food, as you can see, there are so many variations. And these are only just from two different ethnic groups. And there are so many um, other types of food. So unless we have some universal framework, it's going to be very hard to study the physics of food. And so building this universal framework is really the main goal of this course. And then we will apply this universal framework to actually develop a model. So that was about physics, and now we come to physics and modeling. So using that universal framework, once we have developed that, then we can build models that can replicate, that can give us the analog of the real food system. So why do we care for these physics or the modeling? Who needs this? So let's talk about that a little bit. So modeling based on the physics is an enabler and resource builder in all three areas of research, education, and manufacturing. And so, for example, in research, it says how something works, why does it work, how to make it more efficient, learn from previous knowledge. In education, it can provide modeling and simulation can provide interdisciplinary training. So someone who doesn't know all of it, of different physics details, can use the simulator to essentially replicate that same physics without getting into all the details. Then uh, in education, we can have this kind of a varied audience. And so interdisciplinary material can be easily provided using simulation. And we can scale up educational processes, meaning if it is, for example, if there are simulations, web-based simulations, lots of people can use it simultaneously to learn a certain concept. So scaling up is easy. So those are research and education, and then manufacturing is the big context here for the course. So one of them is the design or the doing what if scenarios. what if I change the temperature? What if I change the moisture? What happens? Modeling and simulation based on the physics allows that. Then it also allows realistic prediction of processes and quality and safety. And so let's focus on just the manufacturing part, which is kind of the main reason for a course like this is to relate it to food manufacturing, or as we'll see, digital food manufacturing. So, what do we mean by digital food manufacturing? Digital food manufacturing, of course, there can be many different definitions and many different things are included, but I'm going to talk about just four different things. I've picked just four such items that are often talked about. One is computer aided engineering. Another one is digital twins. You may have heard of it. Then smart appliances and systems approach. So all of these are really heavily being worked on right now, and they all depend on this modeling simulation, which in turn is based on the physics. But first, there so before we get started, we should look at food as having some unique challenges in its modeling and simulation and its physics. Unlike, let's say, metals and plastics, if I may say, in many ways, food has more complexity. What are some of these complexities? Well, one of them is it's structurally complex, and its relationship to sensory is uh, uh, sensory qualities is more complex. There's also high variability, as you would guess, from person to person. So that's one. Then there's massive changes during processing. So think of this bread and what it started from, a dough. There is so much changes in physical properties and all other details, the deformation and so on. Um, so then engineering studies of these kinds of complex processes are more limited. Other materials, I'm afraid, have been studied more. Non-biomaterials have been studied the most, but even biomaterials in the context of human health and so on have been studied more than food as a biomaterial. Then food processing is often multi-physics, so it can include um, fluid flow, heat transfer. If it's being heated in a microwave oven, then electromagnetics, and if it is changing shape and size, which almost always it does, then it involves solid mechanics. So doing multi-physics by its very nature is challenging. So it's no surprise that food process models are challenging. Um, and then, uh, so it often requires this multidisciplinary human resource needs, because food involves chemistry, microbiology, material science, chemical engineering, mechanical engineering, all. So these multidisciplinary human resource needs are often there for food. And then another one that is kind of against trying to build models. Well, you build models to study. It's often very much worth it when the material is expensive and we cannot do too many experimentation and so on. But that is not the case often, that the raw material costs less, which means incentive to build model and simulation is somewhat lower. Okay, so now we have to define this uh, different terms. We said computer aided engineering, as we'll be talking more about it. So what is CAD, computer aided design? What is computer aided engineering or CAE? And what is computer aided manufacturing? So computer aided design would be uh, something like the geometry, okay, of this. Let's say I took the simplest process of canned foods. So computer aided design is going to only talk about the geometry, which is a cylinder. Computer aided engineering, on the other hand, would talk about analysis of some physics involved. So in this case, let's say if we are canning, then it will be heat transfer, and then you can get this kind of a heat map of the temperatures inside the can. So that computer aided engineering includes the geometry, the CAD part, but it also has analysis. Computer aided manufacturing, on the other hand, is basically um, interfacing the actual equipment. So in this case, this is a canner, and that could be uh, controlled by a host computer. So this is what I would call computer aided manufacturing. So three things: computer aided design, computer aided engineering, and computer aided manufacturing. We're making these subtle, making these difference here. Sometimes they're used interchangeably. But for our purpose, we would try to keep these differences straight, and then we would be talking mostly about the computer aided engineering. Now, what is computer aided engineering? So there can be many examples of computer aided engineering. Here I picked a very simple, trivial one, and that is just predicting properties of food. Again, this is a knowledge base that we just created. It is something built for industry in mind. I'm hoping industry would be really picking up on this, and it was a long project. So all the information is here on this website, or you can simply use the QR code. So what it is given, you just think of a food and come to this site, and it gives you an estimate of the property. So these estimates are, of course, based on the physics and some simple models. And these models can even be not physics based, but just data driven models, just a curve fit, but model nevertheless. So, and others can be little more involved, little more mechanistic, partly mechanistic. So here's an example of what can be done. So let's say I want to find a thermal property, thermal conductivity of mozzarella cheese. So from the list, I choose mozzarella cheese, and then I choose from the list of property thermal conductivity. Then I choose the condition, what temperature range I need, and and then these formulas, whether they are uh, more mechanistic or less mechanistic, are built into this database. And then finally, if there is any discrete data available, that is also included. Uh, then the composition of food, once I choose the food here, this one, once I chose the food, the composition is automatically there. But of course, one can change the composition if you're trying to do what if scenarios. And then after doing that, we simply click plot, and it gives me this plot of thermal conductivity versus temperature, which we can export. So I show this for two reasons. One is it is a very simple kind of computer aided engineering. It's basically just relating composition to property, but I also want to share with you in terms of digital resources. In terms of digital resources, this would be a very good one that would match that description, that this digital uh, food uh, engineering or digital food processing and so on would include this kind of a tool. Okay, so let's go on to the next one. Um, so then we get to real, computer aided engineering, the way I was explaining earlier, that you can do analysis together with uh, mm, the geometry and so on. So in the previous example, the analysis was very simple, just to get property. Here it has the full physics, and I'm going to show you a few examples. So one was a project that we had with one of the companies, and it had to do with simulating cake baking. Now you must wonder, why would this company be interested in simulating cake baking? After all, as we know, they don't really sell cakes. But the reason was that in their equipment design, that is their oven design, they want to see how well their design is performing. And one way to do that is to actually bake these cakes, putting them in different locations in the oven, different temperatures, and so on. But that is very time consuming. So they were interested in building this kind of model and simulation so they can try out more conditions more easily. They can optimize the process more easily. Another example was with another company, in this case PepsiCo, where we were looking at how to dry a chip better. So, what combination of drying, how much microwave drying, how much air drying to get the best possible product? Again, these are uh, studies that you can find the full scientific description. But here the point is that companies are very much interested in this modeling and simulation to increase their productivity, increase their quality of product, to get to the market faster, and so on. So those are some of the biggest uses of computer aided engineering in the food industry. Another one where this kind of digital food physics and models which are used in this what we're calling computer aided engineering. Another place for use of these digital models and simulations and the underlying physics, and the use of it is in 3D printing. Yet another one is in AI based applications. So AI based application, and I'll say a little more later, it can actually make some of these computer aided engineering models more useful. And so, for example, their runtime can be reduced from 6 hours to 6 seconds. That's not very uncommon. But to build AI based models, you first need data, and you cannot always have so much data because it's nearly impossible to do that exhaustive experiment. So what we can do is use a mechanistic model, and from that we do the simulation, and then that simulation produces lots of data, and we use that data to train an AI model which would run a lot faster, which means building AI models also need these mechanistic models, which are the physics-based models. So that is another way that digital or food physics and modeling would be useful. So all these are, you can put them in the general category of optimization. Okay, now uh, here we have some more details of this AI based models. So basically, what you can build is a surrogate model. And let me explain what goes on. So let's say I want to model a drying process. So I do a full order model, meaning a full mechanistic model, like you would normally know. It has the physics of heat transfer, mass transfer in its full glory, full details, and you can get outputs. Okay, but the runtime, as you can see, is very large. So what AI based model would do is take this data and then build a reduced order model which replicates this, maybe not perfectly, but then guess what, the time goes down by 2 orders of magnitude or more, actually. So this is coming up as you hear AI based model. And so the digital food physics and modeling would feed to this kind of AI based models. Here I'm giving just a quick uh, sort of a note on how AI-based models can work very, very well. By the way, the course that we are kind of getting introduced to, the course, we are not going to talk about AI-based model. Most likely, it may happen, but most likely not. But I want you to see how powerful these are. So the CNN is one type of AI model. It's the one of the simplest one-step training, and you can see the comparison between mechanistic model, meaning outputs that are generated from a full physics-based model, the kind of model that we will develop in this course, and then comparison of that, how well is that being reproduced by the CNN model, which is in red. So you can see places that there are deviations. And then the deviations improve as we go to another type of AI model, in this case called LSTM, a long short-term memory. You can look up, lots of people are working on these. Then we go to another um, architecture, and this one is the one behind ChatGPT. And look, this is near perfect reproduction. So a near perfect reproduction, and it's going to run 2, 3 orders of magnitude faster. So then AI models would make a big difference in this computer-aided engineering. But to get to the AI models, one of the main sources is going to be these mechanistic models that will produce the data, that will generate the data that will feed into the AI model. Okay, so now we go to the next topic of digital food manufacturing. In this case, we're going to talk about digital twins. What is a digital twin? Now, you can look up, I am not allowed to reproduce videos from YouTube, so you can look up this video. It gives a very nice introduction to a digital twin, but I will just talk about um, digital twin in the food context. So let's say this is meat cooking, hamburger cooking on a grill, and I want to develop a digital twin of this. So what does it look like? So here is a conceptual digital twin. So first we have the physical process. In this case, it is um, the hamburger cooking, and then there is the virtual process that is a model of this hamburger cooking. As you can see, um, how it's changing with time, it's shrinking, and also whatever quantity we're talking about, whether it's temperature, moisture, bacterial um, load, or some quality aspect, it's changing with position. So this is the simulation. So there's the physical and there's the virtual. So this simulation is not a digital twin. I repeat, the simulation by itself is not a digital twin. So let's look at it a little more. Um, so first, the physical system has to be connected to, like, sensors. Let's say temperature is a important variable here, so the sensor could be measuring temperature and feeding to this database. Now this database can also be a simulator. It provides, it can take this kind of input, like what is the temperature, and user input, like am I flipping, how often am I flipping the burgers. It can take these two information, and using the simulator or built-in data already, then it can generate, let's say, what is happening to the safety and quality, or what is likely to happen at the end of cooking. Based on that, based on this simulator results, it can control the actual heat cooking temperature. So maybe the flame temperature is reduced. It is this connection that is absolutely needed for digital twins. So the virtual and physical, they need to be connected together to make it a digital twin. As I said, these are very quick intro. There are papers on digital twin and on food in particular, especially from my Belgian colleagues, and you can look up. Uh, so then this is going to be called the digital twin. So you can see the red dash. This part is now going to be called digital twin. So it has the connections to the sensors, user input, and feedback. This is the important part, feedback to actually control the process. So we can set it up for quality and risk, that is the uh, microbiological risk, um, any other aspects. Okay, so this is also, I want you to see, this is one scale. Hmm. So you can actually go to multiple scales. What do I mean by that? So this part is only for cooking, okay? But the big picture, the entire story of how, where the meat comes from and where it's ultimately consumed, you can start from the slaughterhouse. The process is there. For that you can build models. Then for grinding process you can build models. Then for storage, So during storage, some bacteria might multiply and so on. So you can build models. Then what happens during freezing? How long does it take to freeze? And what happens during freezing quality? You can build models. And then what happens during transportation? What if the frozen burgers, as they're being transported in a refrigerated container, uh, the somehow refrigeration does not work and the temperature increases? Well, the simulator, the the overall simulator or the digital twin can predict what is likely to happen. Then if the temperature in the freezer, that's where the meat is being carried, if that increased, then you know, what do we do about it? How much longer it's going to take to keep it in the freezer so that it goes back to the temperature? And if it got thawed, then there's microbial growth. Then what is going to be the expected microbial growth before we start to cook? Okay. And then after cooking, you store, and there again some processes can happen, and then consumption, where how you're handling things can also make a difference. So the point is, all of these steps, we can build models like the way we're talking about here for just cooking. We can build models, and all of these models can be put together eh, to build a decision making tool or a digital twin of these burgers or the meat from slaughterhouse to consumption, where you can predict in real time which way things are going, if there is something going to go wrong. So then, tying up to this course and so on, all of these models, most of them would need, let's say, heat transfer model, microbiological growth model, or quality model. And that's the kind of stuff we'll talk about in this course. This is a quote that you can read for yourself. Digital twins are of most use when an object is changing over time, thus making the initial model of the object invalid. Meaning, suppose you built a model for transportation of frozen burger. So you can build a model saying, okay, under these conditions, it's going to have this kind of a temperature profile in the burger. But if this condition changes over time, if the refrigeration does not work and the temperature increases, then the initial model of how long the burgers are going to do okay and so on are no longer going to be valid. And that's when measurement data can be used to make this change, capture this change. So what happened? How much was the temperature inside the refrigerated container? And so for that increased temperature, what is going to be my burger temperature? So in other words, we can be continually adjusting in real time, and that's why digital twins are important. Okay, so that was about digital twins and how our uh, food physics and modeling would have to be built into the digital twin. Another example I thought I'd pick up is smart appliances. So when you see smart appliances like that, and it just says potato or vegetable, yes, it can be done again just experimentally by trial and error as to what combination of power and time should I use for vegetable, but understanding it using the food physics and model development, mechanistic model development, these processes would be handled better and those models can be programmed inside the appliances. Um, Next, you can see that this would be particularly relevant, this kind of this kind of a logic of how the cooking would proceed based on certain combination of power and so on would be particularly important and particularly useful in combination ovens like infrared plus halogen or plus microwave, of course. And then here microwave plus hot air, here it's microwave plus grill, and here microwave plus steam. So in these cases, if we build models, then we understand better, and then the models can actually be part of these smart appliances. Final example of how digital food physics and modeling is useful. Final example that I am going to provide is also relating it to systems approach. Again, you must be hearing about this all the time, and that needs what we are talking about, this food physics and the model development. So for example, we can build complex systems approach that combines data driven with mechanistic understanding, and here is an example that I just want to share. Okay, so for example, food, uh, you start from a composition and a structure. From knowing the composition and structure, it's possible to predict raw material properties. It's so we can build mechanistic knowledge base of property composition. Actually, this is the one I showed you earlier in this video. So here you can clearly see this model building going from here to going from the composition to the properties. Now the next level of models are these mechanistic process models. So mechanistic process models can take these raw material properties that have been predicted by other mechanistic models for property prediction, and then mechanistic process models would give me the processed material properties, meaning it will give me the properties of the bread, starting from the dough. It can also simultaneously use energy use databases, and we can combine waste generated databases and food consumption database, and all of these, the mechanistic models that we can build, that we are talking here, can be combined with these kinds of databases to go all the way from composition to raw material properties, meaning the material properties before the food is processed, and then we can get to the processed material properties, how is the final bread, and then changes in packaging and distribution. So during packaging and distribution, what other changes might happen? So it's a systems approach that can be built, but the point here is not these details, it's that these kinds of systems approach are being talked about all the time, and it needs the kind of mechanistic, the physics based modeling and simulation info, to be able to build this kind of systems approach. So to summarize then, this digital food manufacturing that would use some of the digital food physics and models that we'll be talking about in this course. uh, they Four examples we gave are computer and aided engineering, digital twins, smart appliances, and systems approach. So the final comment is this digital food physics and modeling, which is the course we're about to start, is critical in all three areas: research, education, and manufacturing. We discussed that. So in research, it says how, why. In education, it can give interdisciplinary training. And in manufacturing, of course, is the big use, what if scenarios, and realistic prediction of process, quality, and safety. Thank you.